Welcome to EDU World Space.
Hi everyone. What we're going to be looking at is a problem that combines both the concepts of Newton's second law of F equals ma and also the conservation of energy. So the way we're going to be doing this is by first using Newton's second law and the free body diagrams to determine accelerations and use those accelerations in our equations for conservation of energy and kinematics. So what's given to us is we have a suitcase at point A that has a weight of 40 pounds and an initial velocity of 10 feet per second, which comes down this hill from A to B and lands at point C as designated here. We know that the coefficient of friction on the path AB is equal to 0.2, and we also know that the angle of the slope AB is 30 degrees and that the point B is at a height of 4 feet. We also know the distance from A to B is equal to 20 feet. What we're asked to solve for is the distance R, which is the point at which the suitcase hits the ground, which is point C, and we're also asked to solve for the time that it takes to reach that point. So what we're going to do first is draw our free body diagram. What we can do is we can draw our suitcase that is on the slope, which again, as you recall, has an angle equal to 30 degrees. This suitcase has a normal force coming from the slope and a weight force that is acting straight down. And by resolving the components in the coordinate that aligns with our acceleration, which is this direction here, so this is x and this is y, we see that the normal force is equal to W cosine theta, which is equal to mg cos theta. And this was our weight net force balance in the y direction. Next, what we can do is draw our free body diagram for the forces that are acting in the x direction. And we can just go ahead and draw our suitcase, which is again at an angle of 30 degrees. So if we look at the forces that are acting in our x direction, we see we have a component of the weight force that acts in the x direction. And we also have friction, which will be opposing our direction of motion, which we're just going to call FF. Now, by applying Newton's second law, we can say that the net force in x is equal to MAX. And this is equal to the component of the weight force that is in the direction of x, which is W sine theta, minus the coefficient of kinetic friction times the normal force in that which we solve for in our force balance in the y direction. Therefore, when we solve for the acceleration in the x direction, we see that AX is equal to mg sine theta minus mu k mg cos theta, all divided by n. Now we actually know all of these quantities. We know the mass and we know gravity. We also know theta is equal to 30 degrees. So this gives us an acceleration in the x direction that's equal to 10.523 feet per second squared. Now this is a constant acceleration. Therefore, we can apply and use our kinematic equations. Therefore, what we can do is we can say that v squared equals v naught squared plus the total distance minus the initial position. And we also know that velocity is equal to the initial velocity plus acceleration times time. Now we can use these two equations to solve for our velocity at b, at which the hill ends. So what we can do is we can say that VB is simply going to be equal to the square root of v naught squared plus 2a SAB. And I actually forgot to add the 2a here. I'm going to go ahead and do that, plus 2a. And by plugging in these values, we see that the velocity at b is equal to 22.824 feet per second. Now we can use this equation here to solve for the time for which it takes to get to point B. And we can say that VB is equal to V0 plus A T A to B. Therefore, we see that TAB will simply be equal to VB minus VA all over A, which gives us the time to B as 1.219 seconds. Now, as we go from B to C, we can again use the kinematic equations, and since we're moving in the y direction, first we can say that our acceleration will be equal to g, or gravity. So what we can do is we can say that Sy equals Sy naught plus Vy naught T BC plus 1/2 g TBC squared. So this is going to be the time, TBC is the time that it takes to get from B to C. When we solve for TBC, because we actually know all of these quantities, we know that the Sy is equal to 4 feet, Sy0 is equal to 0, Vy0 will be equal to the component of our 22.824 seconds times sine theta, and we know gravity as well. So therefore we can compute TBC to be equal to 0.257 seconds. Remember that our suitcase is also moving in the x direction when it is going from B to C, because it's following that path. Therefore, what we have to do is also compute the distance that it moves in the x direction. So that Sx will be equal to that r, which will be equal to Sx naught plus Vx0 TBC. We find that this is equal to 5.08 feet. So therefore, this gives us a final answer of r that's equal to 5.08 feet, and the total time of A to C, which is equal to TAB plus TBC, and this is equal to 1.48 seconds. So that is also our final answer.